And we show that for the helium atom, because the helium atom has 2 electrons. Okay, so we have to contend with that notion that the electron wave function has now 2 electrons in it. Electron 1, electron 2. And that there is now a combined spin state that we zoomed into last week. So what we have then is, again, the electron wave function for the hydrogen atom is given here. Okay, so we know what these are. There's a radial part, there's an angular part, and this describes the whereabouts, the orbital behavior of a single electron. Okay? And then in that case, we found these states, these wave functions that correspond to orbitals, each with their distinct energy. An important feature was that the energy only depends on n, the principal quantum number, and the L and ML quantum number have no influence on the energy. But that is different as soon as we add more than 1 electron to the system. Okay? Because these electrons interact with one another, and we have to look at things like this. This J indicates electron-electron interactions. It's indicated by this operator, which is a potential energy operator between 2 electrons. And you can see, if we sandwich that operator between the total wave function, the orbital part of the wave function, that we get an estimate of how strong this electron-electron interaction is. This is not completely analytical, but it's a very good approximation, which is why we use it. Due to this electron-electron interaction, we have this situation, which applies to all other elements beyond hydrogen, namely that the energy now depends not just on N, but also on L. Okay, the 2s is lower than a 2p, the 3s is lower than a 3p, which is lower than the 3d. So this is like a little quick recap of things that we already talked about. So, last lecture we said, okay, when you have 2 electrons, there is a combined spin state, there is an orbital state, and the total must be antisymmetric. Okay? For the ground state of helium, we found that this wave function is the only one that actually properly describes the system. And again, let's look at this wave function one more time. I want to make sure you understand why it looks the way it does. Okay? Psi 1, 2, meaning 2 electrons, are being described by this particular function. It has an orbital part, and this orbital part is simply the multiplication of 2 1-electron functions. You see that? Psi 1s for both electrons 1 and 2. So the orbital part of this wave function is simply a product of 2 single electron wave functions, right? Both of them describe an electron in the 1s state. In addition, we have the spin part. The combined spin part of particle 1 and 2 needs to be antisymmetric. That's why there's a negative sign. Why does it need to be antisymmetric? Because the orbital state is symmetric. You can see that, because if you swap the particles, 1 and 2, it doesn't change. Okay? It's a multiplication of 2 things. It doesn't matter if you do it this way or this way, it remains the same. Therefore, the orbital part of the wave function is symmetric, and the spin state must therefore be antisymmetric. That's why this is the only allowed ground state wave function in the helium atom. The other ones are not. Other ones meaning the spin state that describes a triplet state. The ground state of helium is a singlet state. It's not a triplet state. This is just quantum mechanics speak of saying the same thing that you already know. It simply means that the ground state of the helium atom has 2 electrons in the 1s, and they must have the total spin state must be s equals 0, which means paired spins. It's a singlet state. The singlet state has paired spins, okay? And that's what the outcome of this analysis is. Okay, now you can write that out explicitly. So here, the only thing I'm doing here is I'm writing out what does a spin state look like. It looks like this. In terms of the spin states of the individual electrons, this is the form of the spin state of the combined electrons. Okay? This spin state has the desired properties. Well, because if you do particle exchange, you basically generate a negative sign. Now, what we're going to do today is basically write the same thing in a different fashion. Okay? Namely, in this way. What is this? This is so-called a Slater determinant. Okay, we'll define it in 2 seconds. But the bottom line is, this thing here is the same as the line above. Okay, there's no difference. Because these two signs here, these two lines, that basically define this determinant, tell me that I have to do this. Okay? This is the determinant. These two lines mean that's the determinant, and what you have to do is this times that minus this times that. That's what you have to do to calculate the determinant, which has only 4 elements. So we're going to use this a little bit. There's also a homework question on this for this week. And what we're doing is, I'm going to look at this notation here. And the elements of this matrix are basically 1 electron descriptors. Okay? Because it says, in the top row, it basically lists the possibilities what happens to electron 1. It says electron 1 can be in the 1s with an alpha spin, or electron 1 can be again in the 1s, but now with a different electron spin. So when it is in the 1s state, it can have 2 different spin states. That's what it says. And the same is true for electron number 2. The first row tells me the possibilities of electron 1, the second row the possibilities of electron 2. I can, define a shorthand notation for this, which is this. It's called a spin orbital. Basically a combination of spin and orbital. It's the same thing as was on the previous slide, just a different way of notation, which makes it shorter and hopefully somewhat easier to work with. I simply define this spin orbital as psi with an alpha as the superscript, and as the subscript, I define the orbital. So in this particular case, it is psi A, meaning this particle is in orbital state A, whatever that is, the 1s, the 2p, and it has the spin state alpha. Okay? That's what it says. This particle is in the orbital state A and has spin state alpha. And therefore, if I use this notation, also for, this is basically the alternative. If it is having spin state beta, then you write psi beta. So this Slater determinant here describes, once again, the ground state of helium. Okay, so it's just in terms of this new notation. This can be very helpful for us. It's helpful because this notation also works on a larger scale, because remember, the helium atom has 2 electrons, but beyond helium we have 3, 4, 5, 6, 7, and so forth, many more electrons, and it becomes quite hard to write out those wave functions. Okay? But the nice thing about the Slater determinant is that it actually works for an unlimited amount of electrons. The first row describes all possibilities of electron 1, second row of 2, up to whatever number n of electrons you have. If you determine the determinant, you always generate an antisymmetric wave function, which basically is a valid
wave function. Okay? That's why Slater determinants are very useful in chemistry, because they always describe, if they are non-zero, they always describe automatically a valid state of the system. Who has never seen a Slater determinant in their life? Some people haven't seen it. Okay. Well, welcome to the club. Okay, so we'll use this Slater determinants in a moment, but I'd like to basically set the stage for something that we are all familiar with, but now cast in this new concept that we kind of trying to build here in this course. So, the periodic table, as we know, has a beautiful structure to it, right? And of course, the structure of the periodic table reflects the quantum mechanics of the atomic system, right? We already know that because the principal quantum number n are the rows, then you have L, those are different kind of categories, and then you have the MLs, which is basically how many elements you have in one of those categories, which is the S state, the P state, the D state, the F state, and so forth. That just completely mimics the outcome of our quantum mechanical analysis. So the periodic table is structured according to this insight. So the general structure basically mimics the properties of these wave functions, which are the hydrogenic wave functions. Okay? These are the wave functions we can solve analytically, and they play a very important role for us throughout our analysis of atomic properties. The second important ingredient is, of course, this electron-electron interaction, because if you move from the single electron state to a multiple electron state, the approximation that we're making is we can still use those hydrogenic wave functions, but we just add additional effects to it, namely the electron-electron interaction. Okay? That was important because that explains kind of like the shifts in energy. So these are two key ingredients that determine the structure of the periodic table. And then there is another one, of course, which is the exchange interaction, aka Pauli's principle. If you swap the particles, the wave function must be antisymmetric, and that is, again, the same as saying you must pair up electrons if you want to put them in a single orbital state. If you want to put two electrons in a single orbital state, they must be paired, they must have different spin states. These are the three main things, but there's another thing that we have to keep in mind, which is Hund's rule. Everybody is familiar with Hund's rule, but I bet you guys don't know where it's coming from. Why is Hund's rule a thing? Who made it up? Mr. Hund, and why did he do that? So today we're going to try to understand what is that? Where does it come from? Okay? So these three rules already kind of explain the general structure, but they don't exactly explain why I have, for instance, in the second row, in the P block, B, C, N, O, F. Why does it have that particular order? Okay? Well, it has that order because of the atomic, the charge of the atom, but there's another reason for it. Okay? That explains the electron configuration, which is Hund's rule, and we need to know why Hund's rule actually applies. Okay, so I'm going to consider a few cases, and hopefully this will illustrate to you something about electron configurations. Why some electron configurations are valid and other ones are not. So we start with the known case, which is the 2s orbital, right? So let's think of an atom that has electrons in the 2s orbital. 2 electrons in the 2s. 2 electrons in a 2s. And I'd like to design a wave function that is a valid wave function, meaning it must be antisymmetric. So what I'm going to do is, I'm going to use the spin orbitals. Okay? And I'm going to consider this case. I'm going to try, and of course this attempt will be not working out for us, as you will see in 2 seconds, because I'm going to try to put 2 electrons in the single orbital state, which is the 2s state, and I try to make them such that the spin states are identical, meaning parallel spins in an orbital state. This is not allowed, we know that, but I'm going to show to you that you can easily prove that with this later determinant. So, the first row of this determinant is what can happen to particle 1. Particle 1 must be in a 2s state, that's what I'm telling you. In one possibility it has an alpha state, but I require it to have the alpha state regardless, which means the second option is the same. Okay? The second possibility is the same. There's no other possibility. I require it to have the alpha state. And the same for particle 2. So this determinant looks very simple, therefore, because the left and the right elements are the same. The second possibility is the same as the first possibility. I don't want it to occupy the beta state. I want only it to occupy the alpha state. If I calculate this, if I write this out, I get this. Okay? So let's analyze this again. What I see is I have 2 parts to this. The first part here that I'm circling is the orbital state of my 2-electron system. The second part is the spin state of my 2-electron system. The orbital state, as I see here, okay, look at this, is symmetric, because if I change R1 and R2, the product is not changing. Okay? So the orbital state is symmetric. Therefore, the spin state must be antisymmetric. That means that this whole thing is antisymmetric. That's what the Slater determinant does. It ensures that my overall state is antisymmetric. So that's good. But it doesn't mean that this is a valid wave function. Why not? Because look, alpha 1, alpha 2 minus alpha 2 times alpha 1, those 2 things are the same. 2 products just switch. I can just reorder, and therefore this whole thing is 0. The Slater determinant says you can certainly make an antisymmetric wave function, having 2 parallel spins in the same orbital, but the value of this wave function is 0 everywhere. Basically, no chance of having the 2 electrons in that state. Yes?
So then would it be a symmetric wave function? Or
No. This wave function psi12 certainly has antisymmetric properties. Right? It has. Because it's a solution of a Slater determinant, which ensures that it has those properties. But if I do that, if I force it in this state, the outcome is 0. Meaning the amplitude is 0 everywhere, probability 0. It's not a realistic thing. It doesn't describe anything real, because it basically describes nothing. Okay? So, therefore, this shows you, from the principles that we have applied, that putting 2 spins in the same orbital generates nothing. It's not a valid solution. Okay, so now the opposite, of course, is something that we already know. What I have to do is that the first possibility of particle 1 is in the alpha state, the second is now in a beta state. And the same for particle 2. If you evaluate this Slater determinant, then we get what we want. Namely, once more, the orbital state here is symmetric. The spin state is antisymmetric. Okay? And it does not have value 1, because you can see here alpha 1, beta 2, alpha 2, beta 1, those are not the same, even if you reorder them. Therefore, this is not equal to 0, and this has an actual amplitude, which means a valid antisymmetric wave function. The only non-zero solution of this problem is you must pair the electrons. One must have the alpha state, the other one the beta state, as written in this antisymmetric spin state. Does this make sense? Again, it's something that describes something we already know. Something trivial, but I want to show you that this comes from principles that we hopefully can understand on a more fundamental level. Okay, so this is, of course, the conclusion of this analysis. They must be paired. if they occupy the same orbital. This is generally true, because whether it's a 2s or a 1s or a 2p, same. If they are in the same orbital, exactly the same orbital, then the spin state must be antisymmetric. A non-zero spin state. Okay, situation number 2. Please pay attention to this. This looks quite similar, but it's actually rather different. Okay? So please bear with me. Let's try to understand what I'm talking about here. This is key to understanding Hund's rule. Okay, now I'm going to consider 2 electrons in the 2p orbital. Okay, so I have an element that has 2 electrons in a 2p. I want to know what is a valid wave function in this case. So I'm going to consider 2 cases once more. The first one is I'm going to put those paired spins in a single orbital. Okay? Let's call that orbital 2p1. It's just one orbital, and I'm trying to put 2 electrons in exactly the same orbital. Not to be confused by the fact that there's 3 of them, there's 3 states, but I'm not saying that I'm going to use all those states. I'm going to say one orbital of the 2p, let's say 2px, if you like that way of defining them, 2px. Both of them go in 2px. None of them go in 2py or 2pz. Only 2 in the same. In that case, I can say 2p1 is the only orbital that I should consider. That's why all the subscripts are 2p1. First row, possibilities for the first electron. It can be in spin state alpha or beta. Second possibility, second electron, same possibilities. And therefore, this is displayed as a determinant for this case. Let's calculate this thing and see if we get a non-zero solution. If I calculate this, once again, the wave function is always antisymmetric. That's one problem solved. I just need to generate something that's non-zero. Is it non-zero? Yes, it is. Why? Let's look at this again. Again, the orbital state of those 2 particles is symmetric. Because if I swap 1 and 2, it does not change. The product doesn't change. This is an antisymmetric spin state with a value that's non-zero because alpha 1, beta 2 is not the same as alpha 2, beta 1. Those 2 products are not the same. Okay? Therefore, this is a non-zero antisymmetric wave function which is valid. It's yet another way of saying if you try to put 2 electrons in the same orbital, no matter which one, they must have different spin states. The spin state must be antisymmetric, and that corresponds to spin up, spin down. S equals 0. Capital S equals 0. So this is an allowed situation. Situation number 2. Now I'm going to say, well, I do have 3 p orbitals that have exactly the same energy. So what happens if I have 1 electron here in one of them, and the second electron just goes into another p? Namely, this is px, let's say, this is py, and I put 1 in px and 1 in py. Then what? Let's do it. So that's what this says. I have 2, and I'm going to limit myself to the following case. Unpaired spins, meaning both of them have the same spin state. One is in the alpha state in both scenarios, but it could be either in the first orbital or the second one. That's why it says 2p1, and the second option is 2p2. You can substitute the 1 for the x, and the 2 for the y, if you like that, okay? So the electron has 2 possibilities. It goes into the x or the y, or the z, it doesn't matter. Just 2 possibilities. Same for particle 2. So, is this a non-zero solution or not? What do you think? Some people say this. That means yes. This is a non-zero solution, a valid non-zero solution. Let's have a quick look. Here it is. Oh, this looks quite different, folks. Let me walk you through it. Let's look at the spin state here, which is now the first term, alpha 1, alpha 2. That means both particles are always in the alpha state. That is a symmetric state, because if I swap these, the product remains the same. But now look what's between parentheses, this. It's the orbital states. The orbital states and the spin states have kind of switched roles here. That's one way to think about it. Okay, so let's look at that. Let's look at the orbital state now. That's this whole thing. The orbital state looks very different now. See? That whole thing here. It says psi 2p1, psi 2p2, but here it says psi 2p1 for particle 2, psi 2p2 for particle 1. So particle 1 and 2 switch roles. This actually is non-zero. Because if you switch these, you don't generate the same term as on the right. Okay? So it's a non-zero antisymmetric wave function. Which simply means, yes, the wave function that describes one electron in a 2p, the second electron in another 2p orbital, both spin up, let's say, the alpha state, is valid. We know that. You can put two spins in the same state, same spin state, in two different orbitals. That's fine. Question now, which one of these, case 1 or case 2, gives me the lowest energy? Okay, because apparently both are allowed. In one case, spin up, spin down in the same orbital. In the second case, both in the same spin state, but in different orbitals. Both are valid. But the question is, do they both have the same energy or not? Is there a difference between the two? There is a difference. Okay? The first one is actually a singlet state, because S equals 0. The combined spin state has the quantum number S equals 0, which means 2s plus 1 equals 1, which is a singlet state. In the second case, it's in a triplet state. The spin state, S equals 1 now, because I have this spin state, alpha alpha, which has S equals 1, which means 2s plus 1 equals 3. That's a triplet state. It's part of a 3 wave functions that have similar spin properties. The singlet state and the triplet state turn out not to have the same energy. There's a difference. And the key to understanding that is this orbital term. It has nothing to do with the spin. It has to do with the orbital term. Turns out that this wave function, this whole thing, this whole orbital wave function, which describes the whereabouts of these two electrons, if you plot this thing, you can see it. What it shows is that this descriptor here shows that if you try to put two electrons in exactly the same spot here, you get a very low probability. So meaning that it's very unlikely that these two electrons will be exactly at the same spot. Okay? This guy here. It's called exchange interaction. It's a very beautiful quantum mechanical concept. Exchange interaction. Meaning that those two electrons cannot be exactly in the same spot if it's described by this wave function. And that means if they cannot be in the same spot, but they have to be in different spots, and the farther away you put them, the less the repulsion is. If you try to put them in one spot, repulsion is maximized. Okay? This is not true for the orbital state for the top possibility, because there I don't have this restriction. I don't have this exclusion. It turns out that that orbital state, just the product of the two, actually has a maximum in the same spot. So the probability of putting two electrons in one spot, completely allowed, doesn't really go down to 0. Therefore, the electron repulsion of this orbital state is less than that of the singlet state. Therefore, singlet states have generally slightly higher energies than triplet states for the same type of configuration. Therefore, the triplet state has lower energy. And that means that if you have two electrons that basically are in the same spin state in different orbitals, you have a low energy situation, which is basically what Hund's rule tells us. That is the origin of Hund's rule. Okay? Here's the orbital state for the first scenario. Oops. This is it for the second scenario. They are not the same. This is a lower energy state for the orbital state to be in. The second one is slightly higher. This is a very small effect, but it's true, it's real. Okay? And therefore, we can conclude that the triplet state for a similar type of configurations, the triplet states have lower energy compared to the singlet state. Okay, so this is the same statement, but I want to make it specific. The orbital state in the triplet state is antisymmetric, while the orbital state
in the first case is symmetric. Okay? We're talking about these orbital states here, not the spin states. If the orbital state is antisymmetric, lower energy, it's a triplet state. If it is symmetric, which is a singlet state, slightly higher energy. Okay, the next slide is trying to summarize that, and hopefully you understand this. Okay? So, what we're doing, we are saying, if I have a two-particle wave function, and this is true also for 3, 4, and 5, and 6, but the 2 case is more easy for us to understand. Remember, slave determinants can be expanded to n particles, so we have a way to deal with it. So if we focus on the 2-particle situation, we have an orbital state, we have a spin state. They describe 2 separate things. They are not intermixed, they're 2 different things. Orbital state is the whereabouts, the spin state is an intrinsic state of being, independent of the whereabouts. Okay? Please discriminate the 2. I have different possibilities for these spin states to be in. We have seen them by now, and I'm going to list them one more time. Okay? The spin state can be symmetric. Here are the 3 symmetric spin states for a 2-electron system. Okay? We gave them names, sigma plus with a 0, a 1, and a negative 1. Somebody was asking me, what does it mean, the 1 and the 0 here? That refers to the projection of the total spin state. The total spin state is indicated by a quantum number S, capital S. It also has projections, MS, capital MS, and the valid values for capital MS are negative 1, 0, and 1, and that is what that describes. This is the triplet state. The 3 triplet states are defined by their projection quantum number, MS, which can have the values negative 1, 0, and 1, and that is exactly what those superscripts mean. The plus means that it's a symmetric state. If I have symmetric states, I also have antisymmetric states. There's only one of this. We have seen that now. I'd simply give it a negative sign. Okay? The projection is 0. I can put a 0 as a superscript, but I don't need to because there's only one. So why do I put a 0 there? And it's basically this common notation as we see here. Alpha 1, beta 2, alpha 2, beta 1. Okay, that is the spin part. But there is also the orbital part. Okay? If my spin state happens to be symmetric, my orbital state needs to be antisymmetric, because symmetric times antisymmetric equals antisymmetric. Okay? The orbital state must be antisymmetric, and now we have seen what that looks like. It looks like this. It looks very similar to the antisymmetric spin states, but now the alphas and betas are replaced by actual orbital states. It has the same structure, but it describes something completely different. This is the whereabouts of the electron, not its spin. Mathematically very similar, but physically they indicate different things. Okay? This is the antisymmetric orbital state. There's only one antisymmetric one. If I have an antisymmetric spin state, then my corresponding orbital state must be symmetric in order to have a total state, total wave function that is antisymmetric. Okay? Therefore, I have this as a solution, but also this and this, because all of these guys are symmetric orbital states. Okay? As you can see. There's 3 of them. Just like you have 3 symmetric spin states, you also have 3 symmetric orbital states. Okay, this block here is the symmetric spin state, which has S equals 1, which means this is a triplet spin, okay? And all triplet states must have antisymmetric orbital states. All triplet states must have antisymmetric orbital states, otherwise it's not a valid wave function according to Pauli.
the overall wave function must be antisymmetric. And by the same token, the second block describes singlet states, because I have only one antisymmetric spin state. There's three possible orbital states. All singlet states have symmetric orbital states. Okay? This is a natural consequence of combining Pauli's principle with this new principle, which basically is why Hund's rule is valid. If you can remember this, then you are in good shape. Okay? Try to see the flow here. It's only two principles applied, so don't get bothered by the notation. Just try to understand what it actually means. I would just want to synthesize an antisymmetric wave function. So, if the spin state is symmetric, the orbital state must be antisymmetric, or the other way around. Okay? That's what it says. That's all there is to it. Okay, Hund's rule then says the term with the maximum multiplicity lies lowest in energy. That's what Mr. Hund said, but the real reason for this is that the highest multiplicity, in the case of a two-electron system, is the triplet state. The triplet spin state lies lowest in energy because the orbital state is antisymmetric, and the orbital state in an antisymmetric scenario minimizes electron-electron repulsion because of its spatial properties. That's why it lies lower in energy. Okay? And that's an important consideration, folks. In the case of two electrons, that means that the triplet state lies lower in energy than the singlet state. Okay? So, if we combine now this Hund's rule with the other three rules, together we have the Aufbau principle of filling out the periodic table, and we can predict all the electron configurations, not all of them actually, but certainly of the first two rows. Okay? So that's what we're going to do very quick. Here are the allowed hydrogenic orbital states. I'm going to fill them up with electrons according to these rules that we have now seen. I explicitly put the quantum numbers of each of these states to remind you that orbitals really are wave functions squared. Okay? They have labels. These labels come from our mathematical analysis. This is necessarily so. It must be like this because it rolls out like that, and that's where the structure comes from. So, of course, for hydrogen, easy peasy. One electron, we know how that works. It goes in a ground state, it goes, of course, into the 1s. For helium, it goes also in a 1s, but it must be paired, aka the spin state must be antisymmetric. Okay? If the spin state is antisymmetric, then the orbital state is symmetric in this case. There's only one possibility for this configuration, and that's it, and this is the lowest energy. The same is true for lithium, which basically has an extra electron. It must go in 2s. The lowest energy configuration is just this one. The spin can be up or down, doesn't matter, you know that. It can be alpha or beta, it doesn't matter, because they have the same energy. Typically, people draw the up one first and then the downwards. There's no discrimination between the two. Next one, beryllium, 4 electrons. The 4th electron must occupy the lowest available state, which is the 2s, but if it does so, it must have an antisymmetric spin state, which basically means paired spins. That's why it must look this way. The other way is simply not a valid wave function. As we have seen by filling out the Slater determinant, if you try to pair them, you get a wave function that's 0, which means not a valid realistic scenario. Okay, next one, in line. Folks, what is the next element? Boron. Very good. Boron, this one extra electron, must go into one of the p's. Which one? Doesn't matter. They all have the same energy. You can put them in any. All of them are equivalent in terms of energy. Okay, so you can't go wrong there. Typically we start on the left, but that's just because most people read from left to right. That's why it goes there. That's the only reason why. Next, carbon. Here is Hund's rule at play, folks. Carbon, we know, of course, the second electron in the 2p sub level doesn't pair up with this guy here.
Why not? Because this is a lower energy configuration. Because of the anti-symmetric nature of the orbital state, it minimizes repulsion between the two electrons. That's why this state lies lower in energy than the corresponding singlet state. If it would be pairing up, it would form a singlet state. If it kind of like forms two parallel, that means it's the same spin state, that is a triplet state. Therefore, this is lower in energy than the alternative, and that's why this is the configuration that you find the ground state of carbon. Next one, nitrogen. Same idea applies, but this now is like three electron system. Okay, not only two electron system in terms of my analysis, but the same rule applies. Fortunately for us, we basically look at the scenario of multiplicity. This parallel spin scenario has the highest multiplicity, and this analysis can be extended, saying that the highest multiplicity leads to the lowest orbital state in terms of energy, and therefore that's why this is the lowest energy configuration. For oxygen, no chance but pairing up with one of them. Which one doesn't matter, but it needs to pair up. And then it's just a matter of filling out the total n equals to period of the periodic table by just applying the output principle. Okay, so we've talked about Pauli, talked about Hans. Hopefully you understand where these rules come from, okay, and how to apply them. Please remember that slide that I pointed out. If you can remember those two blocks, okay, then you are in pretty good shape. Don't overthink it. It's actually a few simple principles we apply. It's notation that basically catches people off guard, but you can deal with that now, all right? See you on Friday, folks.